Thank you. So I'm relatively new here, and I think most people here do not know what modular forms are and why one should care about them. So I thought I'll give a little introduction to them, and in particular, number theoretic motivation. So let's start with some basic number theoretic question. Let L, Q be an even lattice. And I repeat what this means. So L is some free Z module of finite rank, and Q is a quadratic form with values in Z, which means first property is Q of Rx is R squared Q of X for all R and X. The second property is the map that I define here. This should be a symmetric bilinear form. And I will always assume that we have a non-degenerate lattice, which means if we pair some element of L with all of L, and this is just 0, then S must already be 0. Just to make the, I guess that's a good assumption. And like a typical number theoretic question is now, well, given some integer, is there some x in L such that Q of x equals n? Or directly generalize the question, so given some matrix that I will call T in 1/2 Z to the G times G, is there some x in A to the G such that Q of x, which I define as the inner product matrix, such that this is equal to T. It's like a very basic number theoretic question, asking whether a number is represented by a quadratic form. And like the slightly harder question maybe is, maybe more than slightly harder, what do we know about the representation numbers? About RL of, let's call this M. So these are the number of ways to write M as Q of X. So X in L such that Q of X is equal to M. And of course, we can ask the same question for such a matrix G. And maybe one well-known example. I think I've seen that it's also mentioned in the abstract of the second talk. That's the 4-square theorem. Let L be Z to the 4, Q of x1 to x4 is x1 squared plus x2 squared plus x3 squared and plus x4 squared. then it's obvious only positive or non-negative numbers can be represented, because this is a positive definite quadratic form. And we have for k in z greater than 0, following formula RL of n, k should be m, is 8 times the sum over all divisors of n that are not divisible by 4, and then we sum over d. This is obviously a positive number, so in particular every number is the sum of 4 squares. And the 8 comes from some obvious symmetries on the solution set, like we can always look at minus x, or only change the sign of x1, and so on. Okay, the question is now, how can one prove such a formula? I think Lagrange just shows the existence of such solutions, and as far as I know, or the only proof that I know for such formulas is using modular forms. So that's what we're going to do now. So we first add an assumption that makes everything a bit easier. Simplify. Assume L is unimodular, which means the dual lattice is equal to L, or like the natural map from L to the dual lattice. This is an isomorphism, and not just symmetric. Okay, and for like the first or the next 20 minutes or so, we will always assume that L is positive definite. Yeah, so Q of x is greater or equal to 0, and Q of x is 0 if and only if x is what we call this. Okay, and what modular form people do whenever they see such a sequence, we put them into a generating series. That's maybe very common in number theory nowadays, but we choose a very special generating series. So for t, for tau, in the complex upper half plane, that's the complex numbers such that t is such that the imaginary part is positive. So that will be this part in the complex plane. We can consider the following function, theta L of tau. This is the sum over all lattice vectors. And then we put something in here, U of lambda tau. This is just a shorthand notation for e to the 2 pi I x. Because this comes up all the time, we introduce some shorthand notation. And we can reorder the sum to get the sum from m equals 0 to infinity. And here we have the representation numbers. So we have some Fourier series where the Fourier coefficients are representation numbers of quadratic forms. Okay. So the first observation is maybe let's let's look at this. This is e to the 2 pi I u minus 2 pi I, 2 pi, there's an everything, I m u minus 2 pi m v, if we write tau as u plus I v. So this will, the series will converge in all the nice ways that we want them to converge. Particularly, it will be a holomorphic function. Yeah, and here we explicitly need that the lattice is positive definite. Otherwise, the series would not converge. Okay. Yeah. Then one remark. One can do the same for the matrix things, for the G greater than 1. For this question, one ends up with a generalized upper half plane, the so-called Siegel upper half plane, and it will turn out that the corresponding theta functions are Siegel modular forms. Just want to mention it because this will kind of show up in the end, in the part where I'm just telling you some nice stories. Yeah. Okay. Now we have a function that's defined by such a Fourier series, so it will be obviously periodic. So we have theta of tau plus 1, that's theta of tau. The plus 1 just changes the u to u plus 1, and e to the 2 pi I is 1 periodic, so this is fine. But there's another symmetry of these functions. If we look at this value, then this is just the sum over the lattice, e of minus u of lambda over tau. And then maybe some people remember from some analysis course, I don't know, the Poisson summation formula. This is the same as the sum over L again, but we take the Fourier transform of the function here. And this function is essentially essentially its own Fourier transform. It's really easy to calculate. It's usually some exercise, and it turns out that this is the same as tau to the rank of L over 2 times the theta function tau. That's a short calculation that I won't do here, but it's not hard. So we have a second very nice transformation formula in addition to the periodicity. Yes?
What's the Fourier transform?
What?
What is the Fourier transform?
The Fourier transform. So if you have a function, it's now higher dimensional, to the n, f of x, e to the I hope I did it right now.
And that is f half of y.
What?
On that thing on the right is half of y.
Yeah. Yeah. Sorry. Yeah. Does this answer the question, or I mean, it's some. Yeah. Yeah.
Yes, hello.
Okay. Okay. Then, yeah, as a remark here on uses Poisson summation. here we also use that L is unimodular. Just otherwise one would end up with the dual lattice here. And then everything becomes more complicated, but it still works. Okay.
They still want to think that the brackets xy in there is now referring to some
other standard method. Or maybe one can also take the inner product here that's induced by the quadratic form. I mean, I'm been a bit sloppy here, maybe. Okay. Yes. Okay, maybe then we have two transformations. Let's give them names. We have T tilde, which is just tau plus 1, and S tilde, which is minus 1 over tau. And these two transformations generate discrete subgroup that I will call gamma, which is isomorphic to ESL2Z. And this is, of course, a subgroup of PSL2R. And it turns out that these are just the bihomomorphic maps on the upper half plane. And this isomorphism can be written down explicitly. So for some matrix M in SL2R that we will write as ABCD, it acts on the upper half plane by M tau is A tau plus B over C tau plus B. So via Modular transformations.
Sorry, that particular community being learned by the
By holomorphic maps on the upper half plane. Yeah, and here, of course, T tilde somehow corresponds to the matrix 1, 1, 0, 1, and S tilde corresponds to 0, minus 1, 1, 0. So these are the two matrices. It's an exercise to show that they really generate SL2Z. I guess you have to believe in it. Okay. Now we define additionally some J, M, tau for M in SL2R and tau in the upper half plane as C tau plus D. So if we write M again as ABCD, then one has the following formulas for J and tau. First one is JF of M1 and 2 tau, the same as J of M1 and 2 tau times J of M2 tau. It's a co-cycle relation. And for S and T, for example, we have J of T tau is 1 and J of S is equal to tau. And combining this, all this stuff now, like the whole board, shows the following transformation formula for the theta function. Theta L of M tau is the same as J of M tau to the rank of L over 2 times theta L tau. And here the nx via these Möbius transformations. And we have to say for all m in SL2 Z and tau in the upper half plane. So it's a function with a lot of symmetry. Maybe I will make a little drawing. So it's minus 1/2, half, 1, minus 1. So here's I. This is meant to be a circle. Take these lines up here. Then this area here, this will be a fundamental domain with some boundary problems maybe of the action of SL2Z. So every point in the upper half plane is can be sent by some SL2Z element into this area. And now we can continue this drawing. This down here will be SF, and here we will end up with PF, and here we will minus F. And somehow this formula tells us the values here are somehow similar to the values here. There's a lot of symmetry in there. Yes?
So here it's the thing is that your action is defined on PSL2, but J is not defined on PSL2, right? J function.
I mean the action I've defined it for SL2. The point is that minus 1 acts trivially. So we of course get an action on PSL2, but it's somehow very common to work with SL2. And J should be or it's not defined for PSL2. Yeah, that's true.
So there's a sort of sign negative.
Defined only for even powers.
Yeah.
But it will turn out.
But the rank is always divisible by 4 or something.
By 8 for modular lattices, and yeah, but there will be no odd weight modular forms. I'll say that in a couple of minutes. Yeah. Okay. So we found a function with nice transformation properties, and we will give functions of this type a name, and that's modular form. Modular form of weight K in Z with respect to SL2Z is a holomorphic function in the upper half plane such that the first one is this transformation property. And the second is this in particular implies that F is periodic, so it has a Fourier series, and we assume that there are only positive, non-negative coefficients. So all other coefficients should vanish. Yeah. That's now the definition of a modular form. And we have, of course, seen that theta functions are modular forms. And we have always assumed that the lattice is unimodular. In general, we'll have to choose subgroups of SL2Z and we cannot expect modularity with respect to the whole group. Yes.
So the fact that we single out this J, it seems to me that what you wrote, like somehow you wrote that J is some sort of one cocycle of SL2 with value in H. So is H1 equal to, is H1 trivial? So it's essentially the only one cocycle, and there's no really any sense of considering other, replacing J by anything else. So could we replace J by other cocycles and have different but interesting theories?
I'm not sure. I think there are no more cocycles for SL2.
Okay,
but I'm not sure.
Okay, so the H1 supposedly is trivial. And
yeah. Okay. And one can, of course, also ask what happens if we allow worse regularity properties, like real analytic only, or smooth, or whatever. Or what happens if we also allow negative coefficients? So there's a lot of things that are being done. We will stay for today with this definition. Now let's introduce some more notation. So MK will be the space of modular forms. There's an important subspace which is called SK, the space of cusp forms. These are the modular forms with C0 of F to 0. So they are constant coefficient values. And that has some.
I think you call it A.
Yeah. Thank you. Yes, and okay, we have seen that the theta function is a modular form, and obviously not a cusp form because the constant coefficient is 1, because 0 always represents 0. Yeah. Okay, then I have some remarks, or maybe also the more geometric people. So the first thing is, we can of course consider the quotient of H by SL2Z up to some problems with torsion. This will be a complex manifold. And we can compactify it. To obtain a projective complex manifold X, and particularly it has an algebraic structure, so there's actually a scheme whose complex points are given by this quotient to set up to some torsion problems that we should maybe forget here. And in this case, for example, these are the complex points of the moduli space of elliptic curves, moduli set of the torsion problems. Okay, then second remark.
Sorry, can you repeat this manifold X is a modular space?
Y is the modular space of elliptic curves. Okay. The complex points of the moduli stack and so on.
The tau gives you
The lattice, the
square,
the method. That's essentially the map that gives you the elliptic curve over C. Okay, that's not. The second remark is somehow more geometric interpretation of these modular forms. So let K be SO2. SO2R. Then K is the stabilizer of I in H. I in the upper half plane. So the upper half plane is actually a quotient SO2R mod K or SO2. And we can now consider a character of SO2. Let I K be a character of K. Maybe if we assume that it's some yeah, I mean SO2, the characters of SO2 correspond to integers. That's what the K is meant to be here. So we have always taken something to the power of K. That will be a character of SO2. And we can now consider the following double quotient. And its projection to SL2R mod where in both cases SL2Z acts on SL2R as we know it, and SO2 acts on SL2R as we know, and on C via the character. This, can I finish the sentence? Okay. This will define the line bundle, and the global sections of this line bundle are exactly modular forms of rate K, and does everything correctly. Yeah, that's the geometric. I mean, it has to be a bit cautious, but yeah, ignore the problem.
This like quotient notation is just a quotient, but for a left action, or
Yes, yes.
yeah.
So 2 acts on the, from the right.
Okay.
And yeah, on SL2 multiplication and on C via this character.
Yeah.
Okay. So this defines the line bundle with global sections given by. Okay, that's also some way how to show that these spaces are actually finite dimensional. One maybe has first to extend all of this to the compactification, and then these will be the global sections of this extended line bundle. If one wants to do all of this precise. So in particular, the dimensions of these MKs are finite. And that's the third remark. The dimensions can be calculated, in this case, quite easily. The dimensions are 0 for up K or K negative, and the dimensions are given by K over 12. K equals to 2 mod 12 and K over 12 plus 1 for K not 2 mod 12. So in particular, M0 will be the constant functions. M2 is empty up to the zero function, and mk is one-dimensional and spanned by some function ek for k 4, 6, 8, and 10. And this function ek can also be written down very explicitly. This is 1 plus minus 1 to the k over 2, 2k, b k over 2. And here is a sum from 1 to infinity. Sigma k minus 1 of m, d of m tau. Okay, let's explain all the notation. These are certain rational numbers, so-called Bernoulli numbers. And this is a divisor sum. D divides m, d to the k minus 1. And in these cases, the space is one-dimensional. So if one finds some modular form of this weight, we directly know it must be a multiple of this Eisenstein series. And then we know the Fourier coefficients must coincide up to some factor. And that's how you get formulas for representation in the space. No. A bit slower than expected. I will skip some part and yes, I jump to the now the stuff that's more related to my actual research. Maybe one word regarding this. For the theta functions now, we've learned they are modular forms of some weight. We always know these Eisenstein series. They exist for every weight. And we can look at the corresponding difference. This will then always be a cusp form. And for cusp forms, one also knows very good growth estimates for these coefficients. So in particular, we somehow know how these representation numbers grow. But we do not get exact formulas usually, because the spaces are not one-dimensional. Okay. Maybe I'll give one remark because I've announced it half an hour, oh no, 2 hours ago maybe. It's the so-called Siegel-Weil formula. Which states there's like a linear combination of lattices of theta functions. And this linear combination is equal to some constant times the corresponding Eisenstein series. Yeah, and don't want to explain the notions too much, but O of L is just the isometry group of the lattice, so inversely linear maps that also leave the quadratic form invariant. And the genus of L measures, in some sense, how good a local global principle holds in that case. Yeah, but and this formula holds very generally. And
with the theta series over the tilde.
yeah, of course. Yes. So for these average representation numbers, we also get exact formulas. Otherwise, this is not true. Okay, so now the question, what happens for indefinite? So if L is not positive definite anymore. Do you still need it? Or?
Wait, I ask you a question on this series, right? So on the Einstein series on that side doesn't see L, only is picked up in the weight.
It sees L only in the weight, and of course, okay, if we say it's to SL to G anyway, then it only sees the lattice through the rank. Yeah.
Okay. And this generalizes to the
Higher
single
series.
theta series.
Yeah. This is true in very big generality. Yes. Okay, so what happens for indefinite? I mean, we have seen, I'll just say it. I mean, we have seen that, or there are like several problems. First of all, for indefinite L representation numbers are usually not finite anymore. So neither writing down representation numbers into a series makes sense, nor this sum over the whole lattice would make sense. It would just contain infinitely often the same non-zero constant, so it wouldn't converge. So the idea is the following. Let L be indefinite of signature PQ. We write VR for L tangor R. We can extend the quadratic form to this real vector space. And then we can consider the following set. Of pairs, and these pairs are subspaces of VR, such that the direct sum is V, and we want them to be orthogonal, and we want that the quadratic form restricted to V plus or minus is positive or negative definite. So we somehow introduce a second set, with which we can now build positive definite quadratic forms in the following way. For some element in here, we define Q mu of x as the difference of Q of x Q plus minus Q of x Q minus, and this is the projection of x to the subspace mu plus on mu minus. This will be a positive definite quadratic form. Which is called a positive definite measurement corresponding to mu and q and whatever.
Just so this decomposition is unique up to some isometry or so?
I mean, there are many of these decompositions. It has the structure, I mean, it's a subspace of the Grassmannian, it can be identified, and it's a real analytic submanifold of the Grassmannian. So it really has a lot of geometric structure, this set. The decomposition is not unique at all. We have an action of the orthogonal group of V on it, which is transitive. So that's the transitive action of the orthogonal group.
Okay, so they are isometric. Any such decompositions are isometric.
Yes, yes. Yeah. Okay, and we now define the corresponding Theta function, which has now two variables. V to the Q over 2. That's just a normalizing factor that can be ignored. And now we write E of Q of lambda times U plus Q U of lambda IV. So you remember somehow if here we had Q of lambda before, and if there were negative values, somehow this would have killed the convergence of the series. So we just enforce it to be some positive quadratic form. Here we do not change anything, so it will be still periodic in front of the U, because Q and U is usually not, the values will not be integral, the values of Q and U, but some real numbers that depend on the decomposition. Okay, and this is also not a holomorphic modular form anymore, so it's not holomorphic, but still modular. And real analytic. Yeah. And it has a nice transformation property in the second variable. If sigma is in the orthogonal group of L. So as I said, yes.
How maybe is what Karim also asked, how much dimensional is V? Or does it depend on Q?
I guess it's P times Q the dimension, but I would have to check for Q equals 2. It's definitely 2 P dimensional over R. In that case, it also has a complex structure, then it's P dimensional. Yeah, in the general case, I'm not sure I know what dimension it has. Okay. Maybe Nasser, do you know?
O is kind of opening inside the orthogonal Grassmannian corresponding. So it should be like dimension times dimension minus 1 divided by some. Maybe P, yeah, maybe P times Q is the right choice. I don't know. But
yes.
Is the V that you decompose in fact the VR?
Yeah. So
okay, then the question would make that sense.
Sure. Sorry. That's because.
So you cannot decompose this necessarily over Q, over Z. So before extending.
What do you mean?
I mean, over Z, such a decay, you cannot. I thought that you have this decomposition over your original lattice, but that's not the case.
No. Okay. I mean, decomposing the lattice is much more complicated than. Yeah. No. This is really something over R. Okay. Yeah. So we also have this nice transformation in the second variable, and so in particular this defines the function on d mod O of L, and one should really think of this as an analog of a half-plane mod SL to Z. So this will, I mean, as I said, this is a nice differentiable manifold. It even has a Riemannian structure. For P or Q equals 2, it's even a permission manifold, and it's really or it should be seen as an analog of this upper half-plane mod SL to Z. So since I don't have too much time anymore, I have to skip some things. And let me just mention now the general idea. We have such a function in two variables. What can we do? We can define so-called theta lifts, that are usually defined by phi, or denoted by phi. And this is a map from the space of cusp forms, or one can also try to generalize it. And this f is mapped to reintegrate f against the theta function. And okay, here are some normalizations necessary. But and here we integrate over H mod SL to Z. Okay, and this will, I mean, this gives us a map from cusp forms to functions on this quotient. One might be interested in functions in this quotient, but more generally, one can define more general theta functions that give us all kinds of different such lifting maps. And one very important such theta function is the Cutler-Nielsen theta function. And it's really kind of defined in the same flavor. It's just the difference is that there are some extra coefficients in front of the exponential term, and it's not valued in C anymore, but it's a differential form. Theta function, which we will call theta KML. That is modular of weight K equal to P plus Q over 2. And closed Q form in mu. So in particular, we obtain a map from SK to the closed Q forms on O of L not G. Let's call this lambda Km, and they actually did all of this much more general. They also did this for higher genus. That's the Siegel thing that I said in the beginning. And then you also get theta lift in higher genus, and so on. Yeah, I had to skip one of the interesting properties of this theta function. Or I can say it fast, but there's a very interesting class of totally geodesic submanifolds of D. And the Fourier coefficients of this theta function, their cohomology classes are the Poincaré of these totally geodesic submanifolds. So it has really a lot of geometric properties. It's really nice. Like all of this is maybe in the realm of what's known as the Kiefer program. Okay, then I think I'll just mention one slightly older theorem, like 2 years ago, but it's a very interesting theorem by me and Riccardo Ciffetti. So can of course consider this map into the cohomology of D mod OL, and the assertion is this map from SK in genus 2 to the cohomology. This is injective in the form Q equals 2, and together with recent result of Grenier and Ciffetti. One actually gets formulas for this. The H22 of this is given by the dimension of SK2 plus the dimension of SK1 plus 1. So we get dimension formulas of these cohomology groups in terms of dimension formulas of customers. Now, in the last minute, I just mentioned, okay, why should we be interested in such dimension formulas? It's just some weird manifold. We get some dimension formulas. Why should we care? These in Q equal to 2, there are certain lattices such that, or there is a lattice such that this quotient or a different subgroup is, for example, the modular space of quasi-polarized K3 surfaces of degree 2e, something that Ignacio is working with. So these spaces, in particular for Q equal to 2, have a lot of, they are often examples for modular spaces. So they might be, at least for some people, interesting. And using these theta lifts, one can obtain a lot of geometric information about these modular spaces or more general manifolds and so on. Yeah, and that's all I wanted to say.